All right, let's talk about area. Anyone define area in general? The amount of surface covered, amount of two-dimensional surface covered by a figure. And area has been very nice to us so far. Very nice to us. We hit things like squares, we hit things like circles, triangles, wonderful little formulas to get all those areas, even trapeziums. It was all great. But then a little bit trickier when we come to a random shape. What we have to do. How do we get the area of this random shape? Where is the formula? That's the problem mathematicians always have to face. Okay, so the random shape, well, the random shape I drew didn't exactly look like, well, it's not a function, but definitely could be split up into partial functions. So if I had a function like this, which could be deemed as some part of this, and I wanted to find the area from here to here, let's say this is the function fx, from point A up to point B, there is no formula to get this. That is the problem. Now, if I drew a triangle here, a rectangle here, a trapezium here, I could get the areas for those very easily just by working out the lengths and widths and all the dimensions and working off that. Now, there is no formula because this is changing. Of course, when I see changing, then I'll always think of differentiation, don't I? The rate of change and stuff. Okay. Well, differentiation is to integration, or is to is to integration, which we're about to talk about, as multiplication is to division. It's the opposite. So often integration can be called anti-differentiation. Okay, and we'll really discuss why that is the case in a minute. All right. So where did mathematicians start off with when they were trying to find the area of a shape like this? Does anyone know where they might start? Anyone seen this before?
Can you say that again, sir? Or do you start?
Yeah, where would you start if you wanted to find the area of this shape with no knowledge of integration? Kind of looks like something.
Like the bottom of a parabola.
Okay, so there you go. I've tried to draw it 3 times. So if I split it up into rectangles, I go, well, it's close to this, but not quite, isn't it? It's a bit missing. But if I split it up into more rectangles between A and B, and got the area of more rectangles, so brought that one here and have a smaller one there, and then maybe a slightly bigger one there. It's getting closer. And then I continue between A and B, I just make smaller and smaller rectangles. And then all of a sudden, these small rectangles are starting to get closer and closer to the area, aren't they? So shapes we already know get closer and closer. So there's a visual representation of me making smaller and smaller. So if you make these distances standardized, so for instance, there's 3 distances here, there's maybe 10 distances here. And if you make these smaller and smaller, all these distances A from B to A, and then keep dividing it into smaller and smaller bits, you'll get pretty close to the answer, won't you? So the more rectangles, the better. If you're looking to estimate the area. In fact, if we did an infinite number of rectangles.
Sir, if you were to, is this kind of like where in calculus we make the difference between 2 points really small? Is it like the principle or
limit?
something?
Yeah, limit. Yeah.
Yeah.
Yeah, so
It
yeah,
is?
that's why it's directly related.
Okay.
And we'll talk about that in a minute. Yeah, good point. So an infinite number of infinitely small rectangles would be pretty precise, wouldn't it? So as the limit of these gaps gets smaller and smaller and smaller, eventually you would just get the area. And that was the first way they came up with getting the area under a curve. All right, so let's look at that in practice. Let's take a simple curve that we can get some easy points from. Let's just do y is equal to x squared. So that's y is equal to x squared as our function, or fx is equal to x squared, if you will. And I'm going to just find the area between 0 and 1. Okay? So what is the area under the curve? That's the world's worst spelling of curve. But you get the idea. So that's this area in here. All right, so the very first estimation you perhaps would get for this is going to be clearly if you make that first rectangle, the area is going to be too big, isn't it? Because what's this point up here then? What's this point up here?
I'm not sure. I don't know.
The function is y is equal to x squared, and it's up to 1. So we just put in 1 as x.
Oh.
Yeah.
So it's 1.
Yeah, so it's 1, 1. Yeah, 1, 1 is up here. Yeah, so that's the first. That would be my first point. If you wanted to go to 2, then it'd be 2, 4, and 3, 9, and so on would be the next points on this curve.
And then you're gonna make several triangles, right? And make it a very minimum point.
Yeah, we'll make a triangle. I need to stick with the rectangle because I'm looking for areas.
Triangle, not triangle, sir.
Yeah, I'm going to make several rectangles. So the first estimate of the area is, well, 1 times 1, which is not very good. 1 unit squared. That's not very good. As you can clearly see, this is a lot of area that is taken into account. So I'm going to split it up a little bit more, and split it up into quarters. So every quarter, I'm going to split it up. So we're going to have to take a first quarter here. The next area is going to be this one. The next area is going to be this one. And then the final area is going to be that. So that's going to be a quarter, a half, and 3/4. So I split up into quarters. Not the best diagram ever with scaling, but you get the idea. So as I chopped it up into 4, I need to find these points, because that's going to give me, I already know the width, don't I? I just need to know the height. The width is a quarter each time. Okay, so I need to find the corresponding height. So the corresponding height here is going to be, well, a quarter squared is going to be 1/16. A half squared is going to be, so this is 0.25, 1/16. If you want to put them in, I'll write them here so it's larger. Quarter, 1/16 is the first point. The second point is a half, and then that squared is a quarter. And the next point is 3/4, and then that squared is 9/16. And then the last point is still 1, 1, isn't it? The one right up here. So that's it split up into quarters. Okay, so we have got 4 points now. Now to find the area of these 4 rectangles, it would be a quarter times, well, 1/16 plus a quarter times a half plus, a quarter times a quarter, sorry. So I'd multiply these y values, and each of the widths is a quarter. Hopefully that makes sense. So I'm not going to do that fully out, but that'll be the first one. It's a quarter times a quarter for the second one, and so on. So I'm just multiplying the y values, which is the height, by the width is constant. Okay, and that gives me approximation. I'll do it. The approximation is 0.46875. If I did it in quarters. If I do the same thing with tens, So at tenths, I'm not going to do this out, but if I split it up into 10 different bits, so well, first of all, question number 1, do we expect this to be more or less than this answer if I split it up into tenths?
Less.
Yeah, you would expect it to be less because you're getting closer and closer, because this clearly is these bits are all above, and there's quite big chunks here above. So if you have them in tenths, those chunks will get smaller and smaller, and you get closer and closer to the correct area. Yes. So that's with quarters. If you split it up into tenths, that distance, you get 0.385. If you split it up into hundreds, you get 0.33835. If you split it up into 1,000 different ones, and there's computer programs that can do this for you, 3383. It's getting closer and closer to
1/3.
1/3. Yeah, congratulations. You win the prize. Okay, it's getting closer and closer to 1/3. So the area of infinite numbers of these, as it approaches infinity, is going to be 1/3. So how can we write that in mathematical language? Well, we can write it using, well, we're just adding up, wasn't it? In this first one, we just got the area of 1 and added it to the next, and added it to the area of the next one, which was 1/4 times 9/16, and added to the area of 1/4 times 1. If you add those areas up, you get a total answer. Okay, so I'm going to look down here, and I'm going to go, right, how do I write that mathematically? So I'm going to write that area under this curve is equal to, now you won't like the way I write this, but I was seeking you
rotation and sum and product rule.
Sum and product rule? No. Oh my God. Wow, that's horrible looking, but can we make sense of it? So I'm just letting you look at it for a second and see can you figure it out, and then I'll tell you what each bit means. So think about it.
What does the I represent the bottom of the sigma?
Well, that's going to be me starting to explain it. So see can you figure it out. So the I represents the first interval. This means starting with the first interval. Okay.
Is that like the first term?
Yeah, starting with the first one. Yeah, starting with the first one. This means the sum up as far as n, the number, doesn't it? Adding them all up. So when we had in quarters, we did it 4 times. So n would be 4 times. So adding the sum. Remember sigma? It's not the scary notation. It is just sum of. You just add, you do individual bits. So the individual bit, and then you add the next one and the next one until you have the final term, which in this case was 4. In this case, it's, well, n approaches infinity. So as we said, if we make them infinitely small and keep doing this sum forever and ever and ever, we will get pretty much the precise answer. Okay, so that's the sum. Just adding them all. Okay, and to infinity means we go as far as we, well, infinitely small gaps. Now this is the function with x put in. The first one would be the first interval put in. And that's what we did here. When we did a quarter and we got 1/16 out, we just subbed in a quarter into the formula, didn't we? A quarter into the function to get the corresponding y value, just to figure out what the height is of this bit. So that means just the height. And this then is the number of x, delta x, the base, whatever the base is, whatever the base has been split up into. whatever x has been split into. So the base. So all it's saying really is it's the sum of base times height. Loads and loads of base times heights. It's the sum of it. And depending how short you make them, that's what n will be. Okay? A dude called Riemann came up with this. Okay? So it just means add up all the rectangles you've drawn. So if you've only drawn 4, you go and add 4. If you've drawn infinite, which you won't have done, you add up the infinity of them. All infinite, or 1,000 if you did 1,000. Okay? So that is what this, and so you will see this, sometimes it's called the Riemann, I forget what it's called. The Riemann, oh, it's written in the book somewhere. You can find it. The Riemann, it's not the Riemann integral. Anyway, it's written in the book what it's called. It's done by Riemann. You don't need to know the name of it. But hopefully it makes sense. That's the key here, not learning off who wrote it. Okay, so let's move on to no big deal, something called the fundamental theorem of calculus. All right, let's move on to this. Now, yeah, so the question is, what does it have to do with differentiation? And it's quite, yeah, it's a complicated process to explain how it's exactly, but you kind of alluded to it. We did it in differentiation when those gaps got smaller and smaller and smaller, and therefore we were able to say, for all purposes. So it's all about how do we get that width smaller and smaller and smaller? Because we kind of know how to do the height bit. How do we get the width smaller and smaller and smaller? And how do we write that sum? And that's the crucial thing. So first of all, let's talk about the symbols we have to deal with. And these you have seen before. This thing, letters, function, dx. Let's talk about those. Because sigma has been already used in kind of sequences and series, Leibniz or Riemann, whoever came up with this is the old German S. So it's just an S. It just means sum of. So technically it's the limit of the sums. So what we wrote on the previous page, this bit, that's what that means. The limit of the sums from A to B. Now we already looked at what A and B might represent in our first diagram. So B is actually the upper, the furthest one, and A is the nearest one, if that makes sense. But the larger one subtract the smaller one. So they're called the limits of integration, where you start and stop. With A being the lower limit, and B being the upper. So basically, where to start and stop.
And then you're gonna try to make A and B equal, like, between A and B closest to 0.
No, not quite actually. No. So your question is going to ask. Your question is going to ask, what's the area under these curves? So if we get these two close to each other, you've asked the wrong question. A and B is just like where we had in our other example from 0 to 1. They're A and B. Now the amount we split it up into is dealt with dx actually. That's it getting smaller and smaller as it approaches. You know, this is the width that we say. When you sub x When you sub x into the function, don't you get the height? So if we were just dealing with one of these rectangles, when we sub the x in, f of x it's called, don't we just get the height of that? So when we subbed in 1, we got 1. When we subbed in a quarter, we got 1/16. That's just the height. Okay, so pretty much, this is not how, it's not the technical name for it, it's the height. It's not called the height. It's called the function. We call it the function. But it refers to the height at that particular moment. Also can be called the integrand. But of course, we don't use that. We just call it the function. So we just usually just put the function in there. We don't think about it as the height anymore, but this is where it comes from. The height of all these rectangles. It's all about a rectangle. Now we just need to multiply that by the width. And as long as the width approaches 0, so we can't write just the width. We have to write something that as the width gets is as small as possible. That's where dx comes into. Dx is called the infinitesimal. I should have remembered how to spell that before I wrote it. The infinitesimal. And it kind of makes sense. Infinitesimally small width of x. That's what it means, really. Okay? But it does come from differentiation, I suppose. It's like differentiation. As Badai said, in differentiation, when we had a curve, and we were looking at the rise and the run, we were looking at the triangle, weren't we, in differentiation? That's not a great diagram. But the triangle was an approximation of the slope of the gradient at a perfect point, one point. So it was the run over the rise, wasn't it? Not the rise, dice. Anyway, the run over the rise. The run we referred to as the change in x. The rise we referred to as the change in y. And if the change in x over y, so dy, remember, is the change in x, or the difference in x, or a difference in y, and dx is the difference in x. And as the difference of those, so the difference in y, dy meant, y2 minus y1, didn't it? The difference between them. So as they got smaller and smaller and smaller, like it's gone. As they get smaller and smaller and smaller, that is how we worked out the slope. And the kind of same thing here. Now it's not exactly the same, and I'll explain that on the next page. But dx, you need to think about it as why it's there is because it is the width of that triangle as it gets smaller and smaller. Okay, so hopefully that explains. Now, when you actually do integration, and if you've done integration already, you forget pretty much all this. You forget most of it, and you just think, right, from here to here, I integrate, and if I sub numbers in, I will get the answer for the area. And I don't think about dx being infinitesimally small. It disappears. And I don't think about the function. It also disappears. I just sub numbers in, and then it magically gives us. But this is what it all means. This is where it all comes from. And that's why it's anti-differentiation, because it's the opposite way around if you're looking for area, which I'll explain just a little bit more in a second. Okay, that is the symbols. So these symbols we'll be using a lot in integration. All right. This, when I write it like this, is called the definite integral. Integral. Because there's a definite bounds on it, a and b. So sometimes when we're doing integration, there's no bounds to it. You just integrate and find a general one. There's no upper and lower bounds, and that's the indefinite integral, if there's no bounds there. But it's called the definite integral. An integral means to combine, to integrate. And that's where the word came from. Integration is just another name for combination. And what's it a combination of? It's a combination of a load of sums of rectangles. To simplify it down, all the same thing. So it's not a scary thing. Now, the fundamental theorem of calculus is then that this, the bit in above, b a f x dx, is equal to capital F with b put in, take away capital of F of a put in. Now, this capital F refers to the antiderivative, or the integral. So those of you who did add maths last year will remember getting integration and subtracting. So you did this, I know, Rigel, you did this last year, didn't you?
Sorry?
You did the integration a bit last year, yeah?
Yeah.
So perhaps you didn't learn how it came about, but you definitely learned how to apply subbing in values, and I'm sure you did that. Possibly. Anyway. So, so the derivative of the antiderivative is just the original function. Now, think about that for a second. So this is the antiderivative. This is it. So the step before this. So if I were to derive it, I'll get back to the thing. So hopefully that makes sense. Now, why it makes sense, I'll still talk to you about it in a second. Why this antiderivative works. And it's got to do with, it's obviously got to do with areas. Okay. But this is the fundamental theorem of calculus. And it's basically saying, if you integrate this function and sub in b, and take away the integration of the, or it could be called the antiderivative, so it's integration. If I take away subbed in b and a, I will get the area. Okay, it's quite ingenious how it's come up with. Unfortunately,
Sir, I'm a bit confused about what f of a is. I understand f of b.
Yes, we understand f of b and not f of a. It's the same thing. They're both integrants. They're both anti-differentiations. Now, why this works, I haven't explained. Why it works. Now, hopefully...
So they're like the 2 points, right, sir? Like,
yeah, they're the two endpoints. Yeah, B and A, yeah. This is the B and A.
Okay, got it.
Yeah. You're not subbing them into the function anymore. You're subbing them into the... I'm listening to myself. You're subbing them into the integral of the function, and it gives you the area. But why does it give you the area? And that is the question I'm going to look at in a second. Let's just, before I go into the technicalities of why it does, let's just look at the basic rule of anti-differentiation, also known as integration. It's just the precise opposite of derivatives. So x to the power of n in derivative form will be n times x to n minus 1. And in practicality, x squared then is 2x, isn't it? The derivative in practicality. So antiderivative must work the other way. So x to the power of n, well, if it works the opposite way, this is the way it looks. X to the power of n plus 1. So instead of subtracting 1 from the power, you're now adding 1 back to the power. And then you're going to have to divide by the number that was in front. N plus 1, divide by. So how does that look in practicality? Well, let's look at, so this is derivative, and this is it in reverse. Now that might make sense yet, but hopefully will in a second. X squared. So I looked at x squared being 2x here. Okay, that's the derivative of x squared. But if I wanted to go the other way and integrate it, so go 1 up, how would that look? It would be x, add 1 to the power, n plus 1, cubed, and then divide down by n plus 1. So what's n plus 1? This cubed, 3. Oh, does that make sense? This is it integrated. This anti-differentiated. So in other words, if I differentiate this, so if that is my function, and I differentiate So this is what we did in term 2. If I want to differentiate that, well, let's do differentiation and see this work out. Multiply down by the old power, 3, x, take away 1 from the power, 2, and that's still divided by 3. That cancels with that, and that leaves us back with x squared is what we wanted. So it does work. So what is integration? This is, I suppose, integration by rule, or anti-differentiation. Add 1 to the power, and then divide by what that power is now. So if I wanted to integrate 4x to the 4 over 5, and I want to anti-differentiate or integrate this would give, sorry, these equal signs are, I shouldn't be writing equal signs because of course they're not equal to each other. One is the differentiation or integration of the other. So if I want to integrate this, I'm going to follow my system. Add 1 to the power, x, 5. Still 4x. There's nothing to say to do anything with the number in front. Divide down now by, there is a 5 here already, but I got to divide by 5 as well. So it's going to be 5 times 5, if that makes sense. So that'd be 4x to the 5 over 25 as an example of this. Now, if you don't believe me, you can always test. Just derive this, and I should be ending back with 4/5 of x over 4. So let's derive that. So multiply down by 5, I get 20. Oh, is this not looking right? 20x, take away 1 from the power, I get 4, all over 25. And that, of course, simplifies back down to 4 over 5. So it does work. All right, that is anti-differentiation. Okay, that is what your homework's going to be on, which I'm going to set you off on your way to do in a minute. Well, maybe not a minute.
Example, please, sir.
Sorry?
Can you do one more example, please?
Yeah, sure. Give me anything with x's in it. All right, so let's integrate 3x squared plus 2. Now this, yeah, let's anti-differentiate this because technically it's not fully correct unless you put in something at the end. But anyway, so if I want to anti-differentiate this or integrate this, I need to look at this first term. Add 1 to the power, so it's x cubed. So it's 3x cubed now. And then divide down by the new power. Divide by 3. What about if there's nothing there?
You just add x to it, so 2x.
Yeah, it's just 2. Yeah, so that's x to the 0 if you want to take it as x to the 0. You add 1 to that, divide by 1, and then it's just 2x. Yes. So this would be it. All right. So I've shown you how to anti-differentiate. It hasn't quite explained why it's done. But let's just go back to one of my original questions, which was y is equal to x squared, and we got 1/3 out of that, from 0 to 1, if you remember that old chestnut from about an hour ago. It's an hour and a half ago, my God. If I did the integral of this from 0 to 1 of x squared dx with tiny, tiny, tiny changes, that would look like then, how do I write this? That would then well, let's differentiate x, add 1 to the power, so it's not x squared, it's x cubed, over, well, just divide down by that new power 3. How I write the next bit is put a box around it and say, well, I'm going to do from 0 to 1. In other words, I'm going to sub in 1 and sub in 0, which I was talking about here. Sub in 1, take away 0. Okay, and I'm going to do that on the next page. So I'm going to do x cubed with 1 in. So I'm going to remove the x cubed. I'm going to do 1 cubed over 3. Take away 0 cubed over 3. 1 cubed is 1, isn't it? So this is not 1/3 cubed, it's just the 1 cubed. 1 cubed is 1, so that's 1/3. Take away 0, and that gives 1/3. Hey presto, it worked. Okay, that's the fundamental theorem of calculus. It hasn't been explained fully yet, but it is integrate and then sub in the upper and lower bounds and subtract them. That's all we need to do. That is the fundamental theorem. Now, maybe I should leave this till tomorrow to explain. Well, I'll have a little go at explaining it. Okay, so that, if you pick up nothing else from today, pick up that. Integrate, and then sub in the two values, and then that will give you the area. Okay, but how does this area have to do with gradients and differentiation? That's the question. All right, let's look at something. Let's look at that line. Let's talk about, so this point here is 3. Its top point here is 13. And its distance is 5. Okay, so, yeah, so from here to here, it's 0. All right, so let's just talk about the gradient of this line. A bit out of focus. What's the gradient of this line?
Is it 5/3?
No, this is 3, this is 13, and it's traveled 5.
Oh, so is it 1/2? Or 2?
Rise over run.
Yeah, 2.
2, yes. We got there. Yeah, so it rises 10 for every 5 it goes over. Yeah. So the gradient of this is 2. All right. Let's draw the gradient function. Isn't the gradient function? Ever read that?
Yep.
That's f dash x. This was fx. This is f dash x. All right. Let's refer, so there's 2 little diagrams for it. Let's refer to f dash x. So you two do physics, don't you?
Yeah.
All right. Doesn't this refer to a
Yeah, we
speed? Often if the initial one was distance, yeah? Speed is the distance over time, yeah? F dash x refers to speed, doesn't it usually?
So we're doing kinematics now, sir.
Oh, wonderful. So S, when you have distance and you derive it, it's the speed or whatever, isn't it? Okay. So let's compare what the multiplication of dx means in integration. In other words, fx times dx before the thing. And compare it to dy dx in differentiation. Okay? So let's think about this as a reworking of this is rise over run equals gradient. And we got that smaller and smaller, yeah. This kind of looks like it's talking about the rise is equal to the gradient times the run. A little bit of a reworking, perhaps. In other words, the distance or the area under the curve is the speed multiplied by the time. Okay, so
Yeah.
in this particular case, the time would still be 5 from here. The area under this would be 10, wouldn't it? Or the distance would be 10, yeah. Because we've this is speed and this is time. Perhaps.
This is velocity over time, right?
Sorry?
This is a velocity over time chart because the speed stays consistent. Or, oh no, is this acceleration over time, sir?
No. No, I'm not talking about acceleration. No, I'm not talking about acceleration. I'm just talking about velocity.
The acceleration would be 0 though, right?
Yeah, but I'm not talking about acceleration. Yeah, it would be 0. Are you just showing off your physics knowledge? Yeah, the acceleration would be 0 because it's a flat line now. Yeah, it's no change of the change. Yeah. Okay. So what was the area then? So the area, if we relate it back, is where I start minus where I end. Oh, where I start, where I end. Or the other way around if one is negative and the other. Because where did the 10 come from? The 10 came from 13 minus 3. It's the change here, 13 minus 3. That's where the 10 came from. Now, we work back to this. In other words, we're looking at the differentiation. We want to work back. This is what the principle we're using is working back to that by using this to find the area. And that's the whole principle of the fundamental theorem of calculus. Now that has simplified it down a lot and used this is how we can get a flat surface from one that's not flat, if that makes sense. But it's kind of the inverse of working out the gradient. Now, perhaps I'll explain that a little bit more, but it's quite a difficult concept to explain. There's a whole chapter on it in the book, and I think this is an easier version of what the chapter says. So what I'm going to do for you guys is set a couple of simple questions just on this bit, anti-differentiation, just that much. And I'm going to set you a video that you can watch that might explain this a little bit better, because you both are not physicians. Maybe someday in the future, but physicists, which you are because you do physics, you can figure out, because they do talk a lot about kinematics, which we will do as well this year, but we haven't done yet when we have both integration. So the video I'd like you to watch is that one. And I'll put up the few questions, not many, just it's going to be just a few, just to get you into the realm of it. If you can do both of those for tomorrow, that would be fantastic. And we can pick it up there from there tomorrow. That gives you about 20 minutes.
Wait, 2 videos, sir?
Just one video. It's in the chat. I'll put it on ManageBack as well for you.
All right, sounds good, sir.
All right, see you guys.
Thank you.
Talk more tomorrow.
Thank you, bye.
All right, see you.
So I have a quick question. Are the questions you're gonna put are based about the video? Right?
Not so much. It's more explained.